Okay, is it better? I hope so. All right. So yeah, I'm sorry about that. So I haven't really said anything important yet. Right. So we want to look at. Thanks a lot. At strongly interacting QFTs at finite temperature and also finite density. So as we all know, the finite density issue is quite important for exploring the phase diagram of QCD and phenomena which are associated with hypothetical critical point of QCD, which the future dedicated accelerators such as NICA in Dubna and FAIR in Germany will be looking for, but also RIC has an appropriate program to the vicinity of critical points. And it would be good to say something universal about QFTs at finite density in the regime of strong coupling. So this is where holography can help, and the reason of studying the holographic duals is that this is the only window at the finite chemical potential and finite temperature in the regime of very strong coupling. And of course, there are other applications such as relativistic astrophysics and so on, and just a theoretical interest is also non-negligible. So holography was quite instrumental in providing some insights into transport and strongly interacting QFTs at finite temperature, such as viscosity. And the theories of finite density, as I already mentioned, they were considered starting from 1899, notably in these papers by and collaborators, and so on. And the typical construction for n equals 4 supersonic minerals at finite density, top-down construction which involves rotating black brains. So if you have collection of black brains which are not rotating, but they are non-extremal, you have finite temperature. If you start rotation in 10-dimensional space, then you can introduce chemical potential by going from 10 dimensions to 5 dimensions by reducing on the 5 sphere. And the supergravity, the low energy limit of string theory in dimensions, then reduces to 5-dimensional gauge supergravity in 5 dimensions. And this supergravity has solutions which allow to introduce chemical potentials. So a very special case of the solution which we'll be talking about is the so-called STU solution, which was discovered by Bernd Cvetic and Sabra in 1998, a long time ago. There are different solutions, as I will be talking about STU. A special case of this STU solution is the Reissner-Nordstrom black hole, or black brain, which has a flat horizon, of Einstein-Maxwell gravity. And this was used later on in many bottom-up scenarios since then, because this is a benchmark example of holography at finite density. Now, we will see in this talk that this STU solution is unstable with respect to fluctuations of neutral scalars. So this solution comes in the STU framework with a gauge field, but also with scalars. And the scalars are trivial in this background, so they're equal to 0 essentially. But if you consider fluctuations of these neutral scalars, then you will see pretty easily that this solution is actually unstable. Instability was discussed before in the connection of charged scalars, which also appear in a 10-dimensional setup when you go from 10 dimensions to 5 dimensions, and they're also 0, and you can fluctuate in them. And with the story of holographic superconductor and all these wonderful things, with a construction which goes from below up, it emerged from these considerations. But we are talking about neutral scalars, so this is the ground itself, not the fields in 10 dimensions. Okay, so let me remind you in one slide, what do we do if we have a QFT with a global symmetry group G, for example, for n equals 4 supersonic minerals? This is the R symmetry group, so it's a supersymmetric theory. N equals 4 means it has 4 supercharges, and therefore there is a global symmetry which rotates these supercharges into one into another, and the global symmetry is SU4, it's non-abelian, right? But generically, so suppose we have a non-abelian global symmetry group G. The grand canonical partition function involves a maximal set of commuting conserved charges. So for example, for Sn equals 4, naively you can say, well, I have SU4, so I have n squared minus 1, meaning 15 global conserved charges coming from Neutra's theorem, and I should introduce 15 chemical potentials for for my partition function, but you don't have to do it. I mean, you can do it, but it's not necessary. You can get away with the maximal number of commuting charges in the Cartan subalgebra, and this follows from a very simple calculation of the partition function, which involves a trace, right? It involves a trace. So if I have a trace, and then I have e to the minus beta h, and here is my representation of the group element G, represented by U, then you can insert 1 under the sign of trace, which is u of eta, some other element of a group, u minus 1, right? So this gives you 1, but you can rearrange as much as you can under the sign of trace, and therefore, by homomorphism of a group, so this is u of the product of eta G, eta minus 1. So this is a conjugation of the element eta, and by conjugation you can bring any element to the element of the Cartan, subalgebra, of the algebra of the group. And therefore, in this case, in the case of SU4, you only need to introduce 3 chemical potentials, not 15, right? And this simplifies things very strongly. So if you don't want to do this line of calculation, you can introduce your 15 chemical potentials and then see that they are not independent, right? So there are a relationship between them, which was done a long time ago, in particular in this paper, using a simpler version like SU2 group, for example. So if you want to really feel how it works, you can do it explicitly. So we need only 3 chemical potentials in our case. Now, let's see what we can say about stability. So, long time ago, Einstein wrote one of his less famous, but still famous paper about critical opalescence. That was in 1910. And in that paper, first emerged a formula which tells you the probability of a fluctuation in a thermodynamic system in thermal equilibrium in a microcanonical ensemble, right? So probability of this fluctuation is proportional to the exponent of the delta S, where delta S is the difference between the entropy in the near equilibrium state emerging as a result of some fluctuation and the entropy of the system in thermal equilibrium. So if you have small fluctuations characterized by parameters xc1 and so on, xn, then you can expand. So you have delta S, but S prime is sufficiently close to S, so you can expand in Taylor series. The first term in the non-trivial term in the expansion will involve derivative of S, right? The first derivative of S, but we're at thermal equilibrium, but of course it is 0, right? Because we are sitting at thermal equilibrium, and the entropy is at maximum. But then the next non-trivial term involves second derivatives of S. Right? So second derivative of S with respect to these parameters, and therefore this probability will be proportional to this wonderful expression which contains lambda ik, which is this second derivative, right? So this is microcanonical ensemble. You can do recalculation to canonical, uncanonical ensemble if you want, right? And then the formula will be a similar one. So I would like to draw your attention. So this is all sort of the basic sort of statistical physics of the university course. But I would like to draw your attention, and normally what happens in university courses is that you use this formula and then you compute the probability of fluctuation of, for example, number of particles or charges and so on in your system, right? So this is fine. For us, the interest is to look at the situations when this formula tells you that the fluctuations become extremely large. So therefore, you have some instability in the system, right? So I draw your attention to this matrix, right, which will appear in different incarnations later in the talk. So this is a Hessian, right, the second derivative. And for the stable thermodynamic equilibrium, the quadratic form, which appears here, should be positive definite. Otherwise, these fluctuations will blow up. Okay, that signals instability, right? So I remind you again from linear algebra that positive definiteness of the quadratic form means that the leading principal minors must be positive, right? Not just the determinant. Okay, so then in grand canonical ensemble, so this translates into this formula where the x's will be specifically the entropy density and the densities of our conserved global charges, right? The R charges in n equals 4 supernomic mills, of which there are 3. So we have 4x4 matrix of S and 1 and 2 and 3. And what we'll see that the eigenvalues and eigenvectors of identify the unstable hydrodynamic and dual quasi-normal modes in the gravitational background. So I will tell you about quite normal modes a little bit later. So to see how this works explicitly, so the goal is to develop hydrodynamics with multiple conserved charges and see how thermodynamic instability coming from the Hessian appears in the hydro modes explicitly. And this predicts which gravity modes in the dual picture will be unstable. All right, so that's basically the subject of the discussion. So Pavel Koftin later in this program will tell you more about the development of the hydra with multiple charges, because it turns out this is a fairly involved story. But for now, we can just see what happens when we have an equilibrium state at finite temperature and finite density of just one charge. Okay, so let's just, for illustration, let's talk about one charge only. All right, so what happens? Well, we have one conserved charge and finite temperature, and we expect there is a usual story, right? So they're conserved, so the T mu, the energy momentum tensor is conserved, right? There is a conservation law. There is a conservation law for the current. There are constitutive relations for T mu and for the current, right? You can write them down, you can combine them, you get equations of hydrodynamics. I mean all of this because all of you are experts on this. And then you can write down the dispersion relation for the quasi-particle excitations in this system, which are quasi-particle gapless excitations with hydra coming from the hydra equations of motion. And in quantum field theory, these excitations, these dispersion relations, will appear as poles of the appropriate retarded correlation functions. So for example, if we put our spatial momentum q along z direction, we will have the following hydra modes in this case. The shear momentum diffusion pole in correlators of currents and energy momentum tensor, such as JJ, right? So some components of JJ, and then J and T mu, and T mu, and T mu in the appropriate direction. So this will be a shear momentum mode. This was known before, very well known for n equals 4 super Mills. But in addition to that, the sound and the charge diffusion poles will arise, and they arise together in the correlators in the so-called sound channel, and they will involve the sound mode with the appropriate values of the speed of sound and the attenuation, and also charge diffusion mode. In this case, only for one charge. We limit ourselves to one charge only. So we suspect instabilities, right? If the system is unstable, instabilities will arise in the sound channel. Because here, there is no room for instabilities. We know the ratio of eta to epsilon plus p, right? So this thing will be equal to appropriate value, which was computed in 2006, and there is no room for any instabilities there. So the shear channel seems to be fine from a point of view of instabilities. So we may suspect that one of these things, so instability, of course, in this language will materialize if you have the imaginary part of these modes change in sign, right? So this thing is positive, right, and changes sign to negative. So the pole goes into the upper half plane, the system is unstable, right? So we may suspect that one of these things will be the cause of this instability. Yeah, of course. Mm-hmm. That's exactly right. Yes, but the system may undergo a phase transition, for example, right, and then will be a different phase. So everything is fine up to a certain point, right? Then you discover there is an instability. This instability signals if something is wrong. So this something is actually not so easy to write. It may be a change to different phase, or it may be just the end of the phase diagram, right? So your system doesn't exist there is no equilibrium state beyond this value of mu. This may happen, right? So it's an anomaly, of course. I'm not saying that this is good. I mean, but we need to see where this happens. So let's look at sound attenuation constant. Right, so this part involves the viscosity, the shear viscosity and bulk viscosity, and this is very well known. W here is the enthalpy, so this is epsilon plus P, the energy density plus pressure. And I draw your attention to this other part, right, which only exists when you have non-zero density of conserved charge. So it is proportional to sigma. Sigma is the conductivity of the system. But note one thing. So there is a determinant of the susceptibility matrix, which is related to this Hessian I was talking about, right? So this is the derivative of n, the conserved charges densities with respect to chemical potentials. So determinant of this matrix enters the expression for the imaginary part of both modes. But notice one thing. So in the sound mode, it happily enters as a square. So if it changes sign from minus to plus, nobody cares, right? So it's still stable. But in the diffusion mode, there is no square, right? It's just a determinant, right? So you may suspect already from, and here is a square, right? So everything else is positive. So you may suspect already from this expression that the charge diffusion will be the source of instability. And this is indeed the case. So we'll be talking about n equals 4 with finite density. So let me just remind you, this is a theory, gauge theory with gauge fields, and then there are some scalars and there are some fermions, all in the adjoint representation. Are symmetry, and you can write down the neutral charges, right? So this is a theory which has a Lagrangian, which is always good to, you can do perturbative calculations, right? So one of the things which we haven't done, but it would be in principle good to do, is to fully analyze this theory perturbatively, right, at finite chemical potentials. Partially, this work was done in a beautiful paper, right? So let me say this in words. So we want to consider this theory at finite temperature and finite density. We will be focusing on this theory in 3+ dimensional Minkowski space, in flat space, right? You can also consider the same theory in a compact space. For example, you can put it on a free sphere. And there is a reason to do this, which I will probably mention later, but we won't be doing this. So in principle, you can consider this in a compact space. And the question is very simple. Do we know the equilibrium state for this theory at all values of the ratio of temperature to chemical potentials, including its low temperature limit, right? Or even more brutally, does it exist? All right, so that's even stronger. So if you may help to answer this question, in the limit of infinite number of colors, SUN, and large 't Hooft coupling, but we can also consider a perturbative regime and compare the two, right? So that's a goal, right? Now we will focus here on the scenario A, because scenario B involves Hawking-Page transition, and this is far more complicated, so we don't want to go into that. And the case B was considered at some length by Larry Yaffe and Daisuke Yamada in 2006. And it's a very, very good paper, and I encourage you to look at it. But this was a compact, so this is n equals 4 superintendents on a sphere. Okay. Fine. So I was thinking of maybe including a couple of slides for the benefit of those who are not yet fully indoctrinated in ADS, CFT, and holography. But now I think, okay, let me do it very quickly, right? So this is gauge string duality, which allows you to compute in theories which are very strongly coupled using the dual gravity description, right? So the best description of duality is coming from the slide which was used by Shamit Kasher a long time ago, and I like it very much because it incorporates the whole kind of philosophical message of the duality. You can have some object, and you can view it from either, look face on, right, or you can tilt your head and look it from this direction. And from this direction, it looks like a duck. If you tilt your head, it looks like a rabbit, right? But it's one and the same object. Therefore, duality tells you that you can use different languages in describing one and the same object. So in string theory, this happens. So you have such an object. It's a brane. It's a solution of string theory. Just you can think of similar to black hole, but with flat horizon. So this object arises in open string picture and closed string picture. In open string picture, a low energy limit of the collection of these objects involves a certain field theory, in this case, n equals 4 supersymmetric Young-Mills in 4 dimensions, which has Lagrangian partition function and everything this theory has. In the closed string picture, the same object has a description in terms of the n coincident d-branes, like black holes if you want. And it is described by the type 2B superstring theory on ADS5 crosses 5 background. And this is conjectured to be exact quantum equivalence in the sense that partition function of one theory is equal to partition function of the other theory. But notice this is a strong big duality between a gauge theory with a coupling alpha and the coupling 1 over alpha on the gravity side. So it means that if you have a strongly coupled theory here, you have a weakly coupled theory on the other side, and you compute whatever you want. So this means that you can compute anything beyond equilibrium if you want. So you can compute correlation functions, and any deviations from thermal equilibrium on the right-hand side will be encoded into deviations from equilibrium of the appropriate black hole. And the fluctuations of the gravitational background will correspond to fluctuations of your equilibrium state at finite density and chemical potential, with the eigenmodes of the black hole, which are known as quasi-normal modes, corresponding to the eigenmodes of your system, and they involve the Hydra modes. So the quasi-normal modes, of course, are currently a very prominent subject because they enter the gravitational wave physics, and this is something which is really observed in life, which is quite interesting to see. But for our perspective, the quasi-normal modes manifest themselves as poles of the appropriate correlation functions, retarded correlation functions, and you can analyze the gravity background and just see these poles appearing as the eigenmodes of your dual gravity. And this is what we are going to do in the remaining time. So in the complex frequency plane, what you will see when you analyze this dual gravity background is some distribution of these poles. So these are the poles of your correlation function in the appropriate channel, and the Hydra poles will be gapless. Gapless meaning that at Q going to 0, the omega is going to 0 as well. So here, what we see is the example of a diffusion pole in one of the situations. So this is the end of my, no, sorry, not quite the end. Yeah, so you can extract some physical information, well, physical, let's say, some theoretical information about transport coefficients, such as viscosity, so from these dual gravity calculations. So in particular, for n equals 4 superring mills, you can extract the viscosity plus a correction. So this is the infinite coupling limit, with Hopf coupling is denoted by lambda. So you can extract the limit of infinite lambda, and then correction, which goes like 1 over lambda to power of 3/2. So this is example of a shear viscosity, but you can do this with any other physical quantity which appears from the correlators of the 2-point function, 3-point functions, and so on. So many things were done along this line. So this is the end of this little excursion. And we go back to our main topic, which is the STU background and its fluctuations. So I must say that the background looks quite messy. I'm sorry to say yeah. So it involves, so the 5-dimensional supergravity background involves a metric G mu. Then there are 3 abelian fields, right? So we have 3 chemical potentials. So each chemical potential is encoded on the gravity side by the abelian U1 field. And then there are also 3 scalars. And this will be important. What is also important is the appearance of this Chern-Simons type term in the Lagrangian, which will play some role, but not in this particular talk. Now, the parameters of this Lagrangian has equations of motion, and these equations of motion, they have solutions. So one of these solutions is the STU background of Bern, Cvetich, and Sabra, which is characterized by the non-extremality parameter R+, and 3 charges, Q1, Q2, and Q3, right? And we will introduce some notation. So this is a metric. The metric is almost ADS, but not quite, because it is augmented by this function h, here, here, and here. And function h will be related to our 3 charges. Or if you want, these parameters kappa, which you can think of as normalized charges, or they are also related to chemical potentials. So you can recalculate. So I will often call them chemical potentials. They can be recalculated from the charges. And there is a temperature, of course, involved, right? So what we have is a metric, the gauge fields, right? There are 3 gauge fields, and then there are 3 scalar fields, okay? Hi. All of this is coupled. And if you want to study fluctuations of these things, this is not very pleasant. You can extract all thermodynamics from the background as usual, right? Bekenstein-Hawking entropy is computed very easily. charges, the Hawking temperature, chemical potential. So all thermodynamics is almost immediately available. For us, the most important character will be the equation of state. So this theory is conformal. So equation of state, of course, is epsilon, the energy density, is equal to 3 times pressure, if you want to express it this way. But for the purposes of computing the Hessian, we will write the equation of state in the form which involves the density of charges and the entropy. Right? So this is the equation of state, and from this we will deduce all other consequences. Right? So, but again, so this is super conformal theory. So epsilon is equal to 3p, and therefore the speed of sound squared is equal to 1/3. Right? So this is fixed. Now, immediately you can analyze. So you can compute this Hessian right from the equation of state. You can compute this Hessian and analyze what is the stability region in the language of these 3 chemical potentials, kappa 1, kappa 2, and kappa 3, right? And you can plot this. So the stability conditions, right? So you have to compute the leading principal minors of the Hessian. Actually, it's interesting. So if you try to compute eigenvalues, it's actually algebraically, it's such a mess that it's almost impossible to deal with. But the leading principal minors are very simple, and this is some of them, right? So then we find the stability condition in the space of 3 chemical potentials. So the stability region, so this is 0 kappa, all kappas are equal to 0, right? And then the stability region is shown by orange. And here it is. There is a little maximum here at kappa equals 1, 1, 1, right? But otherwise, so everything else is unstable. Yep. Yes. Yes. Yes, absolutely, yes. They are related, right? So there are minor subtleties in this relation, which I don't want to go into because it's kind of quadratic equation. So there are some, but it's basically yes. So you can do, yeah. Right. So okay. So you have this region. Now notice one thing. Notice this line, which is diagonal. It goes a diagonal on this cube of 3 kappas, and then this region here is the 0 temperature region, right? So this is the limit of 0 temperature in this theory. So what this plot shows is that you cannot, in this theory, reach the 0 temperature, the low temperature region, when you stay in the stable regime, right? There is an instability in between. So you cannot go into the regime of low temperature without encountering an instability. Even though along the diagonal, so here, as you'll see later, your metric reduces to the Reisner-Nordstrom ADS black hole, a black brane, which is thermodynamically stable. All right? It's not a mystery because, of course, it is stable along the diagonal, but if you step away a little bit, your fluctuations, of course, will do precisely that, you will be driven into the instability. All right? So this is kind of philosophical message. All right, so, yep. No. I just mentioned it because it plays a role. So this theory is quite interesting because this Chern-Simons plays a role in terms of other effects, but I won't mention them today, right? So it's. It seems, so this is holographic picture, right? So this is strong coupling. And no, I'm not implying that. I'm implying that the solution, which was known for many years, is not an adequate solution in the low temperature limit. So gravity, right? So gravity describes this n equals 4. Of course, n equals 4 may have a perfect phase, right? But what I'm saying is that the known solution is not describing this phase, right? So and this is a question, right? So what is here, right? So there are yeah. So that's a question. Yeah. Yes. Yeah. This is what we're going to discuss. Yeah. Exactly. Yeah. That's the subject of the discussion. Okay. So let's just see. Let's consider some simplest example because this is a collection of kappa 1, kappa 2, and kappa 3. A generic set of equations is awfully messy. So we can say, we can look at some simpler versions. So for example, let's put two of them to 0. And I must say that I'm talking about kappa 1, kappa 2, and kappa 3, but you can also introduce the SU4 group invariance and recalculate. So instead of, because you may say, why you choose kappa 1 not to equal to 0 and then the rest to 0, it's not invariant statement and so on. You can work in terms of the group invariance. I just choose not to, but it is possible. So it's an invariant kind of discussion. Now, for only one kappa, what happens? So we can compute all parameters of the first order hydra analytically in this case. And this is nice property. So as I said, the speed of sound is 1 over square root of 3. Velocity was computed for all 3 kappas in 2006, so this is known. Bulk viscosity is 0 because it's conformal theory. Then the shear momentum diffusion constant also computed in 2006. And then the R charge diffusion constant actually was computed by us. It's a little bit subtle, but you can get an analytic expression. You can see from this expression immediately that there is a problem at kappa equal to 2, right? So this is exactly what Hydra was predicting us, right? Now, the full set of Hydra modes, remember we had them several slides before, so let's just put the appropriate ingredients of n equals 4 superant Mills for a single chemical potential into these expressions which appeared before and see what they tell us. So they predict the and poles in the appropriate correlation, retarded correlation functions. So there is a sound mode, right, which is perfectly stable, right? You see there is no instability in the engineering. And then there is a charge diffusion mode which will be unstable because of this numerator, right? And then there is a momentum diffusion mode, which was again known before, and this is again perfectly stable. Yep. Yes, yes. Mm-hmm. No, the 3 are independent. Right. Yeah. Mm-hmm. They are still, yes, I mean, they are fluctuating. Yeah, that's fine. Yes, yes. Yes, 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 they decouple. Yeah. Mm-hmm. Yeah. Yes, you will see in a second. So they decouple. Yeah, this is a, right. Right. It's not obvious from what they... Of course, we did. Yeah. Yeah. Yeah, that's right. Yeah. So the the set kappa 0, 0 is a characteristic of an equilibrium state. It's a thermodynamic thing, right? Then you want to analyze fluctuations of this state. Of course, you must include all fields. This is your question, right? Of course, of course. But the other two will decouple, so you, okay? Okay, very good. So then, let's see what happens to our Hessian, right? So the Hessian is explicitly written here. Its determinant is written here, so you can see that it changes sign at kappa equal to 2. And then you can also plot the eigenvalues. So it's a 4x4 matrix. There are 2 eigenvalues which are equal to 1. And then there are 2 other eigenvalues. One of them changes sign, right? One of them changes sign. And at kappa equal to 2, exactly. So this is a characteristic of the instability of the Hessian. So now look at the equations of motion, of the fluctuations, right? So this is a full set of equations of motion. Then you have to fluctuate the fields and write down the equation for fluctuations. Numerically, fluctuations of the metric, the U1 fields and the free scalars are all coupled, and it's a horrible mess, I must say. However, the eigenvectors of the Hessian help to isolate the set of fluctuations the unstable mode couples to. So this Hessian, so I don't want to do this in this example. We will do this in example of 3 equal kappas because it's more explicit. But your Hessian has eigenvalues and eigenvectors corresponding to these eigenvalues. So you can look at the mode which is unstable, right? So for example, lambda 3 is unstable, right? So lambda 3 is the eigenvalue that changes sign. There is an eigenvector which corresponds to this mode. And this eigenvector tells you which fluctuations will couple to the unstable mode. Is it a metric? Is it the all 3 U1 fields, or what scalars coupled to it, and so on? So the eigenvector tells you that, or you can also do a rotation, right, if you want, right? But sometimes you don't have to. So in this case, in this particular case of single kappa, what happens is that the relevant U1 field couples to the metric. So you have the metric and the gauge field coupled and the scalars. But two other U1 fields decouple. So just a fact of life, right? So the two other fields will do the usual thing. So you will have a stable charge diffusion. So there are three charges, right? So one of them will be unstable. The two other, like you can think of red, blue, and green, right? So blue and green will do the usual diffusion, charge diffusion, which is stable, right? They won't do anything, right? So they decouple and they obey equations which were known a long time ago. But the unstable mode will behave badly. And in fact, when we computed this, right, we looked at the literature, and it turned out in 2010, Buchel numerically analyzed the full set of these fluctuations, right, without this thermodynamic and hydro analysis, but just a set of gravitational and coupled scalar and U1 fields. And he numerically found an unstable mode of the type, which of course is what we post-dicted, right? So we have a q squared, and he numerically fitted the coefficient A, which is very close to 1/3, right? So he was very careful in stating that this is 0.33333, right? But yes, right. So this is exactly the hydro diffusion mode, which was post-dicted now by our analysis, and this is just an example. So now, let's look at a more interesting example of three equal kappas. So this is where a Reisner-Nordstrom arises. So you have an STU solution in this case, given by, again, the metric, the equal U1 fields, right? So all of them are given by this expression, all three of them. And all three scalar fields are given by that expression. You can do the change of variables. You can do the change of variables in this background and bring the metric into explicit Reisner ADS Reisner-Nordstrom form. And this change of variables also kills your scalar. It makes them equal to 0 with some exponential representation. So it's more explicit to see that you can claim that once you have kappa, 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 right, your background is actually ADS Reisner-Nordstrom, and it's an Einstein-Maxwell system with no scalars in the background, all right? Now, numerous bottom-up constructions use this background as a basic finite density gravity dual, right? So condensed matter applications of ADS CFT were kind of all focusing on this ADS Reisner-Nordstrom background. So our simple observation is that this is all good as far as the bottom-up construction is concerned, but unfortunately, if we look at the top-down construction, it is unstable, right? So it is unstable with respect to fluctuations of these neutral scalars, which are 0 in the background, but fluctuations will drive you out of stability. So this is a Hessian, and the eigenvalues of the Hessian are, so you can see immediately what happens, right? So lambda 1 and 2, they're equal eigenvalues, and they change sign, and kappa is equal to 1. The two other eigenvalues are not very nice, but you can plot them, and you can see that the two other eigenvalues stay positive. So only these two change sign at kappa equal to 1. Now look at the eigenvectors. So the eigenvectors, which are responsible for the eigenvalues which are unstable, are given here. And you can see. So I remind you the variables, right? The variables were S, the entropy density, which means it couples to gravity metric fluctuations, right? And then N1, N2, and N3, which represent U1 charges. So the unstable guys here, they have all 0 in the entropy entry. And this means that these unstable modes actually decouple from gravity fluctuations, which is a huge relief because gravity fluctuations, of course, are very messy equations. So what you have here is a set of modes with -1 and 1 and -1 and -1, right? So you can rearrange your equations of motion in such a way that only these modes are analyzed. So let's do exactly that. So again, so we have the metric, the gauge fields, and scalars. We consider this is a background, right? The Reisner-Nordstrom background. Then we consider fluctuations. Note that despite the fact that all A's are equal, right? So generically, the fluctuations, of course, are not supposed to be equal, right? And they won't be. And the same holds for scalars. Now, what we do here to simplify our life, we introduce, instead of gauge fields AZ and AT, we introduce this gauge invariant combination of these fields, which is basically the electric field. There are three of them, right, labeled by the I. And then there are scalars, which in Fourier language will be denoted by SI. There are three of them as well, right? So generically, we have coupled fluctuations of the metric, three gauge fields, and three scalars. But as anticipated by the Hessian eigenvectors, you can decouple them. Sorry, what happened? Yeah. So you can decouple them in the following way. So this is again, so this follows from this eigenvectors, but you can also see it in a different way. You can rearrange your fluctuations in the following formulas. So you have the electric field, the U1 field, written in the following way. So introduce some variables which kind of remind you of the center of mass. E1, E2 plus E3, right, divided by 3, and the same for scalars. And then consider your fluctuations on top of these center of mass variables, right? So your fluctuation, so this is just a tautology, right? Tautology, you just rearrange your fluctuation fields, but it's kind of cute because, again, this is dictated by the eigenvectors of the Hessian, but it's also, this is a center of mass variable plus a little fluctuation with respect to the center of mass. And then the equations for fluctuations with respect to the center of mass with Gothic E and Gothic S. I mean, my PhD student was very impressed by Gothic notation, so he, I'm sorry, you can see a lot of, all right. So yeah, I have to. So the horrible mess of the equations of motion of supergravity just reduces to the two coupled linear ODEs, which represent the scalars coupling to the gauge field, right? For each for single I, right? So they decoupled. Still, these equations are not very pleasant, and despite some efforts, we were not able to solve them analytically, even in the Hydra limit, right? Which is an invitation for anyone who, right? Yeah, I mean, it would be nice to, like in case of 1 kappa, we found everything analytically, right? But in 3 kappa case, maybe we don't see something, right? But, right, so we had to do it numerically. What happens numerically? So this is a set of modes, or the poles of these retarded correlators. And here it is shown for two values of kappa, right? Sorry, this is a typo. So this is supposed to be kappa less than 1, and kappa is greater than 1. Kappa less than 1 is shown in blue, and kappa greater than 1 is shown by red. So we focus on the Hydra gapless mode. So it's not very well visible because of this small q. We have to keep it small, but I will show a different slide where it will be more kind of transparent. So what happens is that our Hydra mode, numerically, right, from this set of equations that I showed on the previous slide, it crosses into the upper half plane, right? So the other are fine, but this one signals an dynamical instability of the system. This is more explicit version of the same thing. So what we see is the presence of the diffusion mode, as was predicted by the hydrodynamics, right, explicit formula, and a Hessian. And now it's seen dynamically. When kappa exceeds 1, it goes into the upper half plane, right? So the imaginary part becomes positive. What is interesting is that it stays there for some values of q squared and then goes back. So if you analyze this for q squared, which is sufficiently large, it's stable again. So it goes up and then goes down again. And then for kappa less than 1, it is perfectly stable, right? So there is this instability, and similar to what Buchel was doing 15 years ago, we numerically fitted this d of kappa as c times 1 minus k. 1 minus k can be predicted by Hydra, but not the constant. I mean, constant can be predicted by Hydra if you manage to compute the susceptibility metrics, the conductivities, and so on. And we haven't done this, but it's not impossible to do. Or solve the system of equations, which is the same, dual equations. And c is 0.25, which suggests a number, but again, so this is for kappa, which is close to 1. All right. No. This is closed. This is expansion for kappa, which is around 1, right? So of course, yeah, it could be more complicated expression, but don't know. All right, very good. So basically, this is the story. So I will say a little bit in conclusions. So what we have done, right? So we have constructed relativistic fluid dynamics with multiple charges, including relevant dispersion relations for quasi-particle excitations. I haven't told you a lot about this, just a little bit. That's because Pavel Koftin will tell you the full story later when he comes here in the program. With some generic proofs. So for example, one thing you can ask is whether it is possible generic, because this is, this is not holographic, right? So this is just generic hydro. Whether it is possible to say something generic, something like, for example, a sound mode will never be unstable provided this and that, right? Generically for any kind of multiple conserved charges. So, but here, so we have demonstrated that due to instability, the low temperature equilibrium state of strongly coupled n equals 4 theory is not described by a dual ADS Reisner-Nordstrom black hole, contrary to a widely held belief. So here, again, so we don't know. So to begin with, so let's think of n equals 4 superant mills, right, with 3 conserved charges generically at any coupling, right? So you can analyze it at weak coupling, and presumably, so we haven't done this, and in fact, it would be interesting to see this explicitly, but it's very likely that you will encounter some problems given the fact that typically when you introduce chemical potentials, and this is a supersymmetric theory with no mass terms and so on, right? So you have flat directions. And what happens when you introduce, of course, you may expect thermal mass to appear, right? But then chemical potential usually kills it, right? So, and then, so we haven't done this, but one may suspect and one may argue, perhaps even with some generic quantum field theory arguments, right? That perhaps there is a problem for this theory to have an equilibrium state with finite density at all, right? It's possible, right? It's in flat space, again, not on a compact space, but in a flat space. We don't know. We know from holography that at strong coupling, right, in the limit where holography is applicable, we see that at least for some values of ratio of mu over t, such a state exists. And here, somebody may question this and say, well, how do you know, right? So you analyzed your system of equations which come from 5-dimensional supergravity, that's fine. Have you included fluctuations of 10-dimensional fields, right, which are 0 in the background of the supergravity, but they're not 0 in her, right? So that is possible to ask, right? And so some work in this direction was very recently done by Shiraz Minvola and collaborators. Although his line, if I understand correctly, is slight because he was focused. Historically, it happened that this whole development was, it could have been done in the year 2003, right? But people were interested in the holographic superconductor line, and they went along the line of fluctuating of charged scalar field, because this will give you this holographic superconductor, right? So we don't know, right? We don't know if there are other fields who are completely benign from a point of view of the background, but they could destabilize everything if you include their fluctuations, right? So the simple recipe for this, of course, is, well, take your 10-dimensional background, right? Write down the fluctuations, equation for fluctuations of all fields, right? Just put it on a computer, right? Or compute with a Hessian, whatever you want, right? And just identify who is unstable and what is happening, right? So this, of course, will require some work, but that is a question. So at the moment, we don't know the full answer to this, but at least one statement is that this ADS Reisner-Nordstrom story, which again, it was very popular in discussing the ADS CMT, condensed matter theory applications, because at finite chemical potential, this is what condensed matter is, right? So various low temperature sort of constructions appeared, and as a bottom-up thing and so on. And our philosophical message of this paper, of this work is just that people should be aware of this instability and be more careful in drawing various conclusions for condensed matter physics, because it may happen that this is completely artificial. Right? Yep. Mm-hmm. 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 Yeah. 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 If it is a top-down. Right. But yes, but with Minkowski. Mm-hmm. 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 Our fields in. Mm-hmm. 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 Okay. Yeah. Well, hopefully this is the case, right? I don't want to be too pessimistic about that, but yeah. So we should be aware that we don't. So the theory which we love most in kind of holographic setup. So it needs more work to understand what is the ground state, if it exists at all, right? So that's great. Now. So, and we have shown that predictions from fluid dynamics with multiple charges, they help to establish explicit connection between thermodynamic and dynamic instability in the quantum field theory with a gravity dual, right? So I remind you that a long time ago, there was a story of the Gupser-Mitra conjecture, right, which was historically, it appeared before ADS-CFT developed this formalism with Minkowski space and the Hydra kind of applications, and therefore they haven't looked into this again for historical reasons. But it's clear that one can explore the situations. So with a prediction of the hydrodynamics, one can explore the situations of the Gupser-Mitra part, Gupser-Mitra conjecture, and includes other fields as well, right? So this is Hydra with multiple conserved charges, but you can have more complicated situations with spontaneous symmetry breaking and so on and so forth. And I believe that this can be reviewed, right? And perhaps from a limited perspective, right, of this Gupser-Mitra correspondence, one can see explicitly that this is just a consequence of a relativistic Hydra, right? So it's not, there is nothing to prove, right? It just follows from that. All right, so thank you very much for your attention.
Yes, yeah, including copy paste. So I have a question about this dynamical instability at the Q square. Whether this indicated that there will be crystalline structure develops.
Sorry, which structure? I'm sorry. Crystalline structure. We don't know, right? It's a good question, right? So you may ask, so let's forget about this 10-dimensional possible fluctuations, right? So suppose that there is a phase beyond this critical value of chemical potential. What kind of phase is this, right? So if we kind of think in terms of this Gupser-Mitra story, right? this phase is supposed to be inhomogeneous. So this means that the ansatz, so when you solve the equations of motion of supergravity, you have to put in the ansatz which allows for inhomogeneities. Now, I think this can only be done numerically because it's quite hopeless to solve this system analytically. But it has been done in holography within other contexts. So in principle, one can search for this phase with the appropriate inhomogeneous ansatz, right? But we don't know, right? But you're right. I mean, what emerges most likely is some sort of inhomogeneous state. Or the second option is the absence of an equilibrium state at all, right? So you just reach the boundary of the phase diagram, end of the story, right? So these are two options. Which one is true, we don't know. Yeah, yes, yeah, yes. Yes, yes. Yes, exactly. Yeah, exactly right. Right. So there was a body of work on superconductors, right? So holographic superconductors which has some homogeneous structure. So what I would like to see is a paper. Maybe it exists already, right? We simply haven't found. So what happens in n=4 superconductors, right? So beyond this critical point, right? Is there some structure which appears or not, right? So it would be good to see. I think. Yeah. Yes, yeah. The old, yeah, yes. Well, no, I'm afraid not. I mean, I would love to. So all I can say is that, yeah, you mean this one, right? Well, I'm sorry. So all I can say is that, so this is zero mu. This is zero mu, right? Zero chemical potential. This correction comes from the higher derivative terms in the supergravity side, right? It was computed a long time ago, 2005. Dot here, I think, is hopeless, simply because string theory doesn't give us terms beyond the first corrected alpha prime corrected terms, right? So it's pretty hopeless. Even that is very difficult, right? So in most situations you might find this very difficult. But let me be okay. Let me be more optimistic, right? Look, we have two terms on this side. Look at this side, right? Right? It's much worse, right? In fact, perturbatively, computing in these theories, right? It's transfer coefficients and so on, or the analytic structure of correlators that we coupling is very difficult. Is very difficult. I remember some years ago I tried to extract from Guy Moore a very simple answer. Take lambda phi to the 4 theory. I want to see T mu correlator, right, in the complex frequency plane. What is the analytic structure, right, for lambda phi to the 4? And he resisted for about a year, and he wrote a paper and with some analysis of what really happens, and it's pretty complicated. So it's branch points and so on. Right? So it's yeah. So I must say that the perturbative story is actually quite challenging. But in the perturbative side, there are more tools, right? So here we just have this holography, right? So, right. But on perturbative side, presumably one can do some advances. Yeah. Yeah, and another thing I wanted to say about this is that now you may say, okay, why don't you do the same calculation? So for example, yeah, so the ratio of eta to the s with finite mu is still 1/4 pi, right? Because it's a gravity background. But you may ask, what about the correction? Do we have a correction for finite chemical potential? And the answer is, strictly speaking, no. Even though there were papers, again, pretty long time ago, which claimed to compute it. Let me be diplomatic, right? I suspect that I would be happy if somebody would repeat this calculation and get the same result, right? So that's, yeah, it's pretty challenging, right? So. Right. right? Okay. This one, right? Yes. Mm-hmm. Yes. Yes. I believe so. Yeah, I don't remember if we did this, but most likely yes. Mm-hmm. 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 It's possible, yeah. So we were thinking about how to physically interpret it, right? So in principle, one subtlety is that, of course, this is a supersymmetric theory, right? So you have a equal number of bosonic and fermionic degrees of freedom. Now, you may think that a phenomena similar to Bose-Einstein condensation is happening, for example, right? So it's really in a way that the grand canonical ensemble would not be an appropriate language to describe what is happening, because then so you fix a chemical potential, but the charge will keep coming, right, and condensing, right? It's in infinite numbers, right? So yeah. Exactly. Yes. Yeah. Yeah. It is a possibility, and we haven't explored this, but it would be nice to see, and also to see, as I said, right. So this is a theory with Lagrangian, so you can actually do perturbative analysis, right, and see what happens at weak coupling, right. So whether a similar thing is visible at weak coupling, right, because it's easier. Here it's very hard because you don't even know this new phase, right. So, but yeah. Yeah, it's possible. Yeah. Mm-hmm. Stability region, right? Okay, this one, right? Yes. Yes. Mm-hmm, mm-hmm, mm-hmm.
My first question is: does it apply to so the fact that you have some regions which are unstable? Is it still possible in a theory where you have, for instance, 3 or more abelian charges instead of being, because your charges are say related to a non-abelian group, right?
Yes. Yes. Yes.
You have 3 abelian charges, like
Mm-hmm. Mm-hmm. Yes. Exactly. Yes. That's right. Yeah. Yeah. Mm-hmm.
Do you think that the same can happen in natural?
Yeah, we don't know, right? So it's good that I mean that you mentioned the strangeness and so on, because this analysis with multiple, so hydra with multiple abelian charges, it's a construction which is completely universal, right? It can be applied to, it's independent of holography or anything like that, right? So it can be happily applied to QCD or whatever. So indeed, the current situation is that you have to include all these other charges in QGP, right? So it could be useful, right? So what I'm saying is that in this sense, kind of holography is inspiring. Right? I mean,
expect something like this would happen, like, you have some region where
it's quite possible, yeah, but we don't, because this thing, of course, is specific to n equals 4, right? I mean, this stability region is coming from the equation of state derived for n equals 4 theory, right? So we don't know whether anything similar would happen to other theories, right? This depends on the macroscopic structure of the other theories, right? But it's not impossible, right? So it's not impossible to know. Yes, yeah, of course, yeah. Mm-hmm. Yeah.
calculating the retarded function.
Mm-hmm.
Returns.
Mm-hmm. Mm-hmm.
Elements of T.
Yep.
Stress tensor. So I'm wondering if this is a classical object or quantum object. You need quantum mechanics to calculate the correlator, or you don't need it.
Yeah. So okay. So these are correlators in quantum field theory.
Okay.
Right.
Then this is a classical theory.
No.
It's a quantum theory.
It's a quantum theory. It's a yeah. Yeah. That's right. Yeah. Exactly right. But you know, your quantum correlation function, right, in Fourier space is a function of omega and the momentum, right? Its generic form is not known, right? But you can take a limit of very small omega and very small q, small relative to the temperature, right? And then these complicated functions will reduce to the function which will have a pole, just like I was showing, right?
Oh, this is a classical limit.
It's not a classical limit. No, it's a low energy limit.
Frequency.
Yeah, exactly. Yes. So we know that even the theory like n equals also Brand Mills, what any theory, right, in distant theory with energy momentum tensor in flat space, it will have a hydra regime where the correlators must have these poles appearing in the appropriate limit, right? So it's sitting there, right? Okay. Which black holes? Well, we don't know, right? So this is even worse, right? So it's this is bad enough to deal with. The rotating black holes, of course, will have their own. I'm sure will have their own set of instabilities, right? So it's a huge, like one of the most difficult thing in doing this. It's a pretty simple calculation, but analyzing the literature over the last 30 years was a nightmare. I mean, as people wrote a lot of, so there's a huge body of work on the superradiance, right? So these instabilities related to superradiance of rotating black holes, right? And so, one simplifying feature in cutoff for us was that we didn't consider black holes, right? We didn't consider anything with compact horizons, right? Because otherwise it would be infinite, right? So anything with so your question is, so think of 10-dimensional, right? Supergravity going back to Gupser in 1999, right? Consider a rotating 10-dimensional black hole, right? And then see what happens with instability there, right? And but before that, one needs to read what Minwola was doing because they were doing something very, very similar in 10 dimensions, right? So they stayed in 10 dimensions. So.
And when we treat the spin as a conserved charge, right? So now we have three components of the spin.
Mm-hmm.
They are conserved charges in our theory because they are and they are non-abelian. They complement each other.
Yep.
And we find something similar. We find that the spin chemical potential is bounded.
Mm-hmm.
Right? We don't manage to go beyond a certain value of the spin potential.
Mm-hmm.
And we found that at the boundary of the allowed states,
mm-hmm.
the spin density diverges.
I see.
The density is very diverging because it's nothing what particles the free energy. So there might be some interesting
yes. Yes. Thank you. That's very valuable. Yeah. The hydro. Mm-hmm. Mm-hmm.
The second slide, but if I understood correctly, what you said is that if I have a C4, there are 15 charges. When I look at the thermodynamic partition function, I can use rotation.
Yep.
So that all of them except 3 are non-zero. And if I want to work with all the 15, I can just rotate back the solution to the thermodynamic solution. It would only depend on these Now, when I go to hydro, I would expect all these 15 to be able to fluctuate independently.
The state, yes, this is a case. My feeling is that even then, I mean, we haven't done this. But even then, I think it is possible to use the group properties to tame, or shall we say, to reduce this system of appropriate fluctuations, to decouple them, so to speak, right? So, because I don't know if that is indeed the case, but my suspicion is that somehow the group structure should be very robust with this respect, right? So I don't, yeah, maybe, yeah, I don't, yeah. Possible. Yep. That's quite possible. Yeah. Yeah. We haven't. Yes. Yeah. Okay. Sorry. Normal. Unstable. Yes. Yes. That's right. Yeah, that's a good question. So it's a good question for some other topic, right? So here, so the Schwarzschild black hole, right, has a negative specific heat, right? As this is a property of typical systems in asymptotically flat space, right? So it's a solution asymptotically flat space. It evaporates, right? So it's a Hawking evaporation. Now here, with ADS-CFT duality, our black holes or black brains, they live in asymptotically anti-de Sitter space. So in that sense, they're stable. The specific heat is positive, all right? So for us, the instability is a dynamical instability which is not related to the specific heat. If specific heat were negative, right, that would show in this expression for the speed of sound, because you have the Hydra mode. So again, so there's a little subtlety, because when you talk about Schwarzschild, right, it's a compact thing, right? So then strictly speaking, you don't have a Hydra regime because it's a compact, right? So but you can consider black brains which are asymptotically flat. And then you can say, well, I have a specific heat which is negative, right? How do I see this in the Hydra language? And the answer is, you will see this in the sound mode, crossing into the upper half plane, because the speed of sound, which is related to the specific heat via the equation of states and so on, will develop non-zero imaginary part, and this imaginary part will be positive. All right. So there was a paper on that by Alex Buchel a long time ago, around 2005 or 6, where he looked at some within holography in some theory precisely when the speed of sound developed the linear term in the sound mode developed the imaginary part. So this is an example of. No. Yes, yeah, no. Yeah. It is there. It is possible to compute the appropriate coefficients for the what is called the kappa thermal resist coefficient, which is characterized as heat conduction. Yeah, this has been done for one charge, for one not free, for one charge in 2006, but not for free charges. Yeah, that's a good thing to calculate. Yeah, we haven't done this. Thank you.